Alright, it's time to start today's webinar. First of all, a warm welcome to everyone who joined. My name is Niels Verdijk and I will be your host today. Apart from being your host, I'm also one of the customer support engineers at Diabatix. So basically that means if you have any technical questions or you do a project with us, you'll for sure get in contact with me again. That's enough about myself. Let's move on to today's webinar, which is maximizing PCB cooling efficiency with fast concept generation. Last webinar we've mainly focused on the fast concept generation, and today we'll apply it to a PCB application. Rest assured, for those who missed last month's webinar, we will repeat. I will at least repeat some of the concepts behind the fast concept generator. I think that's enough time we spent already on the first slide. Let's move on. So for today's webinar, I plan to talk about the following topics. So first of all, of course, an introduction for those who don't know Diabatix yet. Then we'll move on to the fundamentals of heat transfer in PCBs, how natural convection is used in PCB cooling, and then we'll apply that knowledge, that learnings, to a real-life application where we focus on the thermal management of a PCB. Afterwards, I will discuss any questions that you may have. By the way, throughout this webinar, if you have any questions, feel free to put them in the public or private chat boxes. Our moderators are following along, so they will answer already some of those questions. Any very interesting questions or any unanswered questions, I will try to cover at the end. And lastly, of course, if you like what you see, you want to try CallSim for your own, I will provide you with some information on where you can try it on your own. As ever, let's try to keep this within the 30-minute mark. And that's about it, so let's jump right into it. First of all, why do we exist? What is the core, or what is the main thing that we want to achieve with Diabatix? As you all know, especially within the PCB world, the power generated by those small chips increases every year, following Moore's law, of course, making it more and more challenging to meet the thermal requirements. And that's where we want to focus on. So at Diabatix, we believe that the thermal problems should not be a problem anymore, or at least that it shouldn't be a hurdle that is being tackled towards the end of the design stage. So we at Diabatix, we focus on we develop smart algorithms, and we make those smart algorithms available to any engineer to use thermal designing throughout their entire design process. So as I mentioned, not anymore towards the end, but right at the start. Ansys and Hexagon, two of the biggest names within the CFD world, have acknowledged the strength of our smart algorithms, have reached out to us, and as of recent, we are their technology partners. Alright, let's move on to the fundamentals of heat transfer within PCBs. So as we all know, the electrical currents within the PCBs, or the materials that are being used within PCBs, are not superconductors. So any electrical current that flows through them will have some resistance, and hence when there is resistance, there is of course heat generation, and that heat needs to escape to the environment. There are three modes that the heat can, or three paths that the heat can follow. First one being conduction. So conduction happens in solid materials, basically when the molecules are fixed within a certain grid. And the heat is basically being transferred from one molecule to another by those molecules vibrating, one a little bit more than the other one. They bump into each other, and then the next molecule, the slower moving molecule, has now a little bit more energy that it can transfer. This is what's called conduction, and is being influenced by something called the material thermal conductivity. The higher the conductivity, the more easy those molecules can transfer the heat, and thus the easier the heat can transfer from basically one side of the chip, one side of the PCB, towards the other side of the PCB. And the easier it is, the lower the temperature difference across the PCB. Alright, so now we have the heat has transferred through the PCB and through the housing, and eventually it has to escape to the air, and that's where convection is the dominant effect. What is convection? So convection happens in media where the molecules can move around, and it's mainly affected by the surface area and of course also the fluid properties. So once a molecule of, let's say, air is in contact with our housing or PCB, the PCB will transfer some of that heat. That molecule captures that heat and then flows away, leaving space or leaving the possibility for another molecule to transfer the next batch of heat. So that's the main difference between conduction and convection. With conduction, the molecules are fixed, or somewhat fixed, while in convection, the molecules can freely move around. Lastly, we have radiation. You all know it, of course, from the sun, and radiation doesn't need any media to transfer the heat. So it can transfer heat basically through a vacuum by emitting infrared light. But it is less significant unless you have very high temperatures, which of course should be avoided. This effect can usually be ignored in PCBs. So we'll mainly focus on conduction and convection. Alright. So natural convection, that will be the main driving force, or that will be the where the heat will eventually escape to. And today, or this slide, sorry, I want to cover more what are the mechanisms of natural convection, what factors, what affects natural convection, and how the design considerations affect it. So as I mentioned already, mechanisms of natural convection is the moving of molecules, and the molecules capturing the heat and then moving it through some other space. How is the placement, or the how is the positioning, the topology of the PCB? How does it affect the natural convection? First of all, if you put your PCB horizontal, you of course provide a very big space, a very big area that blocks the air from cooling it down. As you all know, the warmer the air gets, the higher it rises due to what's something called buoyancy. So ideally, your PCB is not placed horizontal, but it's placed vertically. You have a much smaller area blocking the flow, making it easier for the flow, for the air to convect the heat away. Also, on top of the PCB, of course, you have your chips, and they need to be placed accordingly. If your heat sources are behind, for example, plugs that again block the flow, that will affect how easy the heat can escape to the environment. So best practices is to put the PCBs in easily accessible spaces. And that's then of course part of the design considerations. Alright, I think that is more than enough. Let's now that you know that knowledge, let's now apply it, let's now try to find a heatsink that can carry the heat away. On the left-hand side, of the slide, you see the conventional way of working, where, let's say, you have a given PCB layout. So you have your PCB with a given layout of chips, and all of those chips produce X amount of heat. And on the outside of the housing, you have some space to place some fins or pins or whatever cooling structure that you desire. What you would do first is to create, of course, initial pin design, either based on what you see in literature or from previous experiences. Then you run a CFD simulation, or you do physical experiments to know what the performance is of that design. You post-process the results, you analyze it, and then you loop through this until you get a solution. That's the conventional way of working. By using smart algorithms, you can boost the output significantly. In a first step, that's an early on in the design cycle, You can use, for example, quick concepts to get, in a matter of minutes to hours, 100 to 1,000 different designs, giving you great insight into what design change affects the performance. So then you know how far you are from the performance goal, from the temperature goals. If you're very far, for example, if you exceed it by a huge margin, then you know whatever design that you put on it, it will never work, and then you'll have to revisit the positioning of the chips, either remove a couple of chips or choose more expensive chips that produce less heat, or vice versa. If you're very far below the temperature limits, so you have quite a bit of margin still, you can consider reducing the overall size, make everything a bit more compact, which in general makes it more difficult to cool them down. Okay, so that's the concept generator phase, so early on in the design cycle. You can then move on to a more detailed design process to get a final prototypable design. And you can use, for example, one of those concepts to help the optimization process move faster to the final design. Okay, and for today's webinar, as was mentioned in the title, we'll mainly, of course, consider the fast concept generator. So quick reminder, it's very fast, it takes only a couple of minutes to an hour max to get 100 to 1,000 different designs. And this is a sneak peek of what it looks like in our software called Coldstream, but I'll discuss that in more detail later on in the webinar. You might think it's very difficult to do, but not at all. In our software, it only takes a couple of steps. The first step is always to upload the geometry, so your PCB, the layout of the chips, the thermal pastes that connect the chips to the PCB, etc. Oh, sorry, not to the PCB, to the housing. All that needs to be prepared beforehand in your favorite CAD environment. You export it to STEP and you upload it to Coldstream. Next, you set the solids and fluids. For example, you let Coldstream know what thermal paste is being used, what the material is of your chips, etc. As well as what the coolant media is, usually air, but if not, you can, for example, also put water or water glycol, whatever you prefer. Next, you set the boundary conditions. First of all, how much heat does each of the chips produce? Is it forced convection or natural convection? For example, with air, you can put a fan, that is forced convection, or you can solely rely on the heating of the fluid to drive the fluid motion, and that's called natural convection. Alright, then you set your design domain and your targets. The design domain basically dictates what volume is open to generate those structures, to generate those concepts, and the targets let Coldstream know what to optimize for. In PCB, for the PCB, of course, maximize the heat exchange efficiency, and that's pretty much it. So once you complete all 4 steps, the Coldstream knows enough, and it will start generating those concepts for you. And here again, some sneak peeks of what those concepts can look like. Of course, not all concepts are useful to you. For example, 3D gyroids or split P elements may look very fancy, but they require 3D printing to be made, which makes it very expensive to manufacture. So usually for PCBs, die casting is a more suitable option, as it's very cheap for mass manufacturing. And then for die casting, you can specify or you can fine-tune the settings to meet your die casting capabilities. For example, you can specify what the minimal and maximal structure width should be, what the release angle should be to easily get it out of the mold, etc., etc. So you can fully, whatever Coldstream output will meet those manufacturing constraints. Okay, I think I spent quite a bit of time on the explaining the application and giving an introduction, of course. Let's now apply it to a real-life PCB cooling example. In this slide, I give a quick summary of the application itself. So we'll of course use castable aluminum. The chips, there are 7 of them, as you can see here. In total produce nearly 20 watts of energy. We want to minimize the temperature, of course, or equivalently maximize heat exchange efficiency. And we'll use fins and pins. That's unfortunately not correct on the slide. Fins and pins as a cooling concept. And then here you see your design domain, but more on that in Coldstream itself. So let me quickly switch. Where is Coldstream? There. And let me. Yes, you can still see Coldstream. Perfect. This is our software Coldstream, and the main landing page that you get to after logging in is the project overview. As it implies, gives an overview of all the different projects to keep everything as organized as possible. I will scroll down here to this project folder. Yes, inside of your project folder, you can then create as many cases as you would like. And the cases, what I mean with that is the engineering problems that you want to solve. Coldstream supports 3 types of cases: custom design, standard design, and simulation. Simulation is just a regular CFD simulation. If you have a design and you want to know its performance, you can easily do so in Coldstream. But if you want to use generative design, if you want the software to generate something for you, then you'll have to use either custom design or standard design. Where standard design is the concept generator, so where it can. This is the case, or this is the type of case that is used early on in the design cycle. While custom design, that's a type of case where you get a very custom design to your application, as it implies, and it's more suitable towards the end of the design cycle, where you want to make a fully prototypable design, which extracts the maximum out of the performance. But for here, we're in the early design stages, so let's consider standard design cases. And I created such a case. Once you create a case, Coldstream will ask you to upload a step file. I will skip that part and move straight to a case that already has a step file. Yes. And once your step file has been uploaded, you can see it in the GUI here in the middle. So you can look at it from whatever angle that you prefer. And on the left, you then see your regions tree. So all of these entities were predefined in MyCAD environment. And then the only thing to do on Coldstream is basically to click on each of the entities and fill in the information. So starting with the thermal paste, these of course connect the chips towards the housing to make sure that there is no air gap in between, because as you know, air gaps are very bad for thermal conductivity. So the thermal pastes, these are of course a solid, not a fluid, so I will select solid, and then you can let Coldstream know out of what material they are made. For example, as you saw, it's made out of a certain Bergquist thermal paste, and then I provided the properties belonging to that material. If you have any custom requirements, you can easily create those custom materials by filling in the information, and that can easily even be anisotropic if you so desire. Alright, that's enough. For the pastes, everything below is optional. For example, if they were transparent, you can enable radiation. If they, for whatever reason, produce heat, you can add it as a source. Or if the pastes rotate for whatever reason, you can also add rotation, which of course in this case is not applicable, so I'll leave those blank. Same with the housing, the lower part of the housing, that basically screws into the top part of the housing. It's a solid made out of castable aluminum, A380 to be more precise. Then we have a PCB, again a solid, and here I'll use aluminum 6061 to model the thermal behavior of that PCB. We then have the upper part of the housing, which is again a solid made out of A380. We have our chips, which here are made out of copper, And to localize heat production, I defined small subregions, so basically a region for every chip, where I then add a source. For example, chip 3 in total produces 0.56 watts of energy, chip 6 produces nearly 2 watts of energy, etc, etc, etc. And then we have some trapped air in the upper and lower parts. As you can see, those regions are incredibly thin, so thin that basically you can neglect any buoyancy or any buoyant behavior, where we simplify it a bit and just assume it is solid. But then of course the properties of air. Alright, so that's all of the solid bodies. Next we have our surrounding air body, the fluid, the body that eventually drives away the heat, of course. And it's of course is of type fluid now, where we will use air as the surrounding media, and where we then enable buoyancy. So buoyancy enables then the natural convection, the driving motion due to the heat up of the molecules. Here we specify the environmental conditions, so we'll use atmospheric conditions, 1 atmosphere and 20 degrees of environmental temperature, and we then specify the gravitational vector pointing in the negative z direction. So if we have a look like this, this is the correct positioning of our PCB. So the green arrow represents the z-axis, and here we specify the gravitational vector being pointing downwards. Alright, and then we allow an opening on the bottom with again environmental temperature conditions, and an opening to the top where the molecules can leave, and then on the sides we will assume that this is a repeating geometry. So on the sides we impose slip conditions, where basically the flow, the no slip condition, sorry, is imposed, and that's equivalent to using a symmetry wall. Alright, so that's solids, fluids, and the boundary conditions. So the first 3 steps. Next we have to specify the design domain. The design domain specifies the volume where ColdStream is allowed to modify the geometry. And you can let ColdStream know what kind of structures it can consider. For example, if you want CNC millable options, you can choose between circles, circular pins, diamond shaped pins, or rectangular fins. If 3D printing is an option, you can consider gyroids, Schwartz elements, split P, etc. For die casting, you can consider circular pins or rectangular fins. And for sheet metal forming, you can consider circular or rectangular dimples. In this case, we considered circular pins and rectangular fins as options. So I will specify those, and then I can specify my manufacturing settings as was shown in the slide deck earlier. After let ColdStream know in what direction the pins are being generated, I specify Y, so along the yellow arrow, meaning that the structures will generate from the bottom here towards the top on this face, basically. And those pins or fins are made out of a 380. Okay, so that's solids, fluids, boundary conditions, and design domain. The last thing we have to add is to let ColdStream know what to optimize for. That's where our targets come in. So I could add a target on every entity. Simply click on Add Target. Where, for example, here I could minimize the weight. So minimize, make it as light as possible. In this example, we are early on. We mainly focus on the thermal aspects. So I will only put 1 target on the chip, and that is to minimize the temperature. So basically, maximize my heat exchange efficiency, get my heat as efficiently as possible to the air, and that's sufficient. So with all of this input, ColdStream can start computing, and after a couple of minutes to a couple of hours, you then get your finished cases. I propose to first look at the fin options. Yes, So for this case, Colson outputted 99 different iterations, as you can see here on the right. And if you have a look at the Design Evolution tab, we can have an overview of each of those designs and their performance. So the overall design performance on the x-axis has the iteration counter. So basically, it's a timeline of all the iterations that are made available, and it should really be seen as such, as a timeline. And on the y-axis, you see the performance value. I'll disclose that in more detail later on. And then every iteration, of course, has a single dot representing the performance on that graph. If a design is infeasible, for example, I put a weight constraint and it were exceeded, then that design will be infeasible. If it's blue, it means at this stage it's a feasible design, but it's not the best one. And if it's green, it means at this stage it is the best design. So in our case, iteration 1, which at the time was the only iteration that Colson knew about, was a feasible design, hence it is green. Iteration 2 is again feasible and is better than iteration 1, so it's green again, all the way towards iteration 87, which is the last green dot, hence the best iteration, the best design that was attempted. And if we scroll down a bit, we can then see what solution was attempted by Colson. 87 different fins with these dimensions is the best design that Colson found. Perhaps if we go back to an early design with only 2 fins, it's of course immediately clear why this is a worse design compared to the 87th iteration. If we scroll down even further, we then see all of the individual targets that are being used. Of course, in our case, it's only one, the temperature minimization objective, and this is a graph representing that performance and that evolution of the performance measure. Seeing as this is the only objective, this graph is identical to the overall design performance graph. If I were to have multiple targets, the overall design performance would be a weighted sum of each of the objectives. Alright, let's move on to the pin design. Here, exactly the same. So Colson only tried 97 iterations until it was satisfied with all the designs. And again, you'll then have a performance graph or an iteration graph that highlights how each design change affects the performance. Again, our first couple of iterations don't produce a lot of material, only one pin in this example, while our best design, or 33rd iteration in this example, has a lot more pins, and of course is also better performance-wise. But which concept is now the best one? We have pins, we have fins, but how do they compare to one another? That's something that we can easily do here if we put them all in the same comparison view. Yes. If the entities are named the same, Colson will put them on the same line, and then I will select the best fin design, so our 87th iteration, and our best pin design, the 33rd iteration. And then we can compare temperatures. On the left we have the fins, on the right we have the pins, and as you can see immediately, the temperatures of the chips are slightly better with fins compared to pins, which of course is not surprising, as we know from literature that fins, in natural convection cases at least, perform better compared to pins. So now we know that with fins, that's the way to go forward with if you want to maximize the thermal performance. I do see that we are running out of time, so let me quickly switch back to the slide deck. Where is my slide deck? Here is the slide deck. Yes. Unfortunately, I'll have to skip the Q&A session and go straight here. If you want to try Colson for your own, there is a access to a viewer-only account where you can look at finished cases at your own pace, even download those results. Or if you want to know more about how Colson can be used for your team, feel free to email to info@diabatix.com or just ring this number. Thank you all for your time. I wish you a very pleasant day, and I hope to see you in the next webinar. Bye-bye.